So last talk of the day, Matthias Keller, who came in from not quite as far away as Adelaide, but still pretty far away, University of Potsdam, and he's speaking on Cheeger's inequality for graphs.
Thank you for the introduction. So, I think the first time I met Dodziuk was like 10 years ago at a very similar event as this one. And in Germany, like your PhD advisor is called your doctor father. So it's like your doctor father, your academic father. And but next to your doctor father, you also have like other people influence you. And I like to call it academic uncles. So that's like very few people who have like a very strong scientific impact on you during the time when you're still shapeable and you're academic kid. And Dodziuk was one of these very distinguished people for me. Especially in the sense that sort of this interplay between like continuous and discrete things, sort of like this question, what's really going on? What is the same and where you really have phenomena which result from the difference of the underlying space? I think there Dodziuk was a big inspiration scientifically, and also like benefited a lot from his kindness. When I was a PhD student, I was in Princeton, and he invited me over, and we had like these discussions, and he introduced me to Radek, and I got an academic cousin. So, and like there, it resulted in a very fruitful collaboration over the years. So, therefore, I'm very grateful, and today I'm going to talk about Cheeger inequalities on graphs, and that's definitely the most cited paper of yours. Like it's. And I think by now it has like 135 citations on MathSciNet. So I put this like on Cheeger inequality, on Cheeger's inequality. On graphs. So and of course, it started a bit earlier in Cheeger in 1969, and the situation I want to look at here. So, if you have a Riemannian manifold, and here, I want to assume it's non-compact, but complete. So, and the Laplace-Beltrami operator, which I use as a positive operator, and so then if you look at Cheeger's constant for the manifold, which is sort of the infimum over sets S, and you look at the area of S and divide it by the volume of S. And so S would be sort of, like there are two manifolds, right? So like there's one torus and the other one which is continuous here. So this Cheeger's famous inequality, you take a sort of a submanifold S with a boundary, and this S is now a compact manifold, and that's sort of the unbounded part. And you take the area of S and divide it by the volume. That's the Cheeger's constant, and then you can estimate the bottom of the spectrum.
Wait, what S satisfies the info over set of S is satisfied by there's any compact S?
No, well, like you want to define sort of an area, so they have a smooth boundary.
Yeah.
Right.
Yeah, it just carves out a compact.
Right, it carves out a sort of like, you would say that's the compact submanifold.
Oh, I see.
With like
separating thing.
Right, it's separating like a compact piece. So you would take something compact here, right?
Area of
the boundary of S, right?
Yeah.
Right. And then, like you have this theorem of Cheeger from '69, telling you that the bottom of the spectrum of the Laplace-Beltrami is larger or equal than h squared divided by 4. So, so you have You can read this as a spectral estimate, as an estimate on the bottom of the spectrum, or you can read it as an upper estimate by a spectral quantity on a geometric one, how well so if you can separate the manifold. And when you want to do this for graphs, so then there's like all these questions. So if you know what a graph is, you sort of have to determine what is the operator. Then you have like in this Cheeger inequality, you sort of want to know what the area is, what the boundary is, what the volume is. So there are a lot of questions which you sort of have to answer. And there's this for graphs. So, and here I just do the plain vanilla case. So I just take combinatorial graphs. So you have a vertex set and an edge set. And you can also look at weights, but I don't want to do this here, so I might mention it in between. Just looking again, very good. Yeah. We use this later.
Where is it?
Yeah, so you just have a vertices, and they are connected by edges, and if you have sort of a connection, I write x is connected to y. And so if you have functions on the vertices, you can define a quadratic form, which is, that's the energy integral, and so you sum over all pairs of vertices which are connected by an edge, and then you would take this difference. And well, you can understand this as sort of the gradient of that. And this half here, that's sort of a convention, and we will see this coming up in constants later. That's just that you sum over every edge only once. Right, so then, so I think that's sort of the natural analog of this Dirichlet form. In the sense you cannot really take a limit here, so that's sort of the difference is as close as two vertices get. So now if you have a quadratic form, if you want to have a Laplacian, you have to choose a Hilbert space. And in order to choose a Hilbert space, you have to choose a measure on your set. And one of the most natural, or like the first choice would say like just the volume. So what is the volume of a subset? And you can just count vertices. Right? You sort of say the volume of W is just sort of the number of elements in here, or you can just take the constant function 1 and count x and W. And that gives you a scalar product. So if you can take functions, and it's just sort of and I just look at real world functions here. And then you have this L2 space, which is sort of with respect to the measure, the counting measure 1. And this gives you, like, if you close this form, you look at this, you can plug in every function here. So this might give you infinite, but it's a positive sum, so you can restrict it to compactly supported functions and close this form in this Hilbert space, and then you get an operator, and that gives you the operator's Laplacian. Seen before, so the sum of all y f of x minus f of y. And so that's this operator, which corresponds to this choice of the measure. So, and this operator, it's bounded. Maybe I have to erase this when I use the projector. So, this is bounded if and only if the vertex degree So the vertex degree, that's just sort of the number of neighbors at x. So that's just sort of the number of y which are chased.
Can you run a little slowly and bigger?
I tried, okay. So is this that big enough or you want? So, so whenever your vertex degree, your geometry is somehow bounded, this gives you a bounded operator. Otherwise,
We should finish the statement.
ah, okay, there's a, right, that's kind of, thank you. So, and this guy, we give this a name, we call this M, sort of, that's the maximum vertex degree. So now we have an operator. So next you need, we have a volume, so we need a notion of a boundary. And sort of a very natural notion of a boundary is the following. You just take all the edges, how do I write these here? That's what we write them. Just like these pairs. The x is in W and y is in V minus W. So you have to set W, and now you count like all outgoing edges as a boundary. And one way of measuring this area. So, since we are counting vertices, we could say, well, these are the number of x such that xy is the boundary. You could also actually count the y's here. It's just another notion of a boundary. But that's sort of one choice. And then you can define Cheeger's constant for this graph, and I denote this by 1 here. So you take the infimum now over all finite subsets. So, and you take the area divided by the volume. So you have an analog of this theorem. And now that's this result by Dodziuk in 84, that the bottom of the spectrum of this Laplacian is larger than h1 squared divided by 2. Well, and this that you have a 2 instead of a 4.
Is it 2 or 2m?
2m. Thank you. That was for the punchline. Yeah, it's 2m, right? Sorry. Yeah. So I was so focused on the 2. So this 2 doesn't really matter. It's sort of this 2 is just this 2 here. So that's sort of like it's like morally the same as the 4. It's just sort of. But you have another m here, and this m. Well, let me just show you that you actually need it. So it's sort of like an additional quantity, but if you look at the TK, the K regulatory, then you can actually compute the bottom of the spectrum. So just by lambda Laplacian K, and that's sort of K plus 1 minus 2 square root of K. So you get K regular trees, so if you have K forward neighbors. So that would be T2. So, and you can also compute this Cheeger constant, and this would be actually K plus 1. Okay, K or K plus 1, I guess it's
If you took the graph of the grid and the plane, okay, M would be
Right. M would be, right. M would be 4.
M would be 4. What's K there?
That's the
How many neighbors?
how many forward neighbors you have.
Oh, I see. Well, this is for the tree.
That's for the tree.
Okay.
For the lattice, you know that the bottom of the spectrum is 0, and
Right.
also Cheeger's constant is 0. So there it's
That was, I took K equals 4 and I didn't get 0.
right. Yeah. So the Cheeger
It's not supposed to,
constant.
it's not a tree.
The Cheeger constant is K, and M is K plus 1.
Alright.
So so you somehow see, well, that if you square this, then you should divide by K in order to get the correct estimate. All right. So, but now let's do the following. Let's take a look at, put a TK here and a TK square. So we sort of attach to a K regular tree a K squared regular tree. Oh no, let's see, it's more even. Let's not be stingy. Let's take power 4. And let's call this graph GK. Then if you look at the bottom of the spectrum of this graph here, well, the bottom of the spectrum will be sort of assumed here on this side. So that's the same as this one. And Cheeger's constant is also here on this side. Because sort of the boundary values you get here are much smaller. However, this M of GK, M of TK, that's now not equal, but it's put it here. It's power 4. So now what do you see if you look at this estimate? Lambda K of GK, well, that's now MK GK. So that's like more or less K. Like this guy would be also K square. And you have here K over 4. So that's like 1 over K squared. So while this goes to infinity, if you send K to infinity, this goes to 0. So there is sort of something here which this estimate doesn't see. And it's sort of really is caused by this factor. That if you have some part where this vertex degree grows, it might spoil the whole estimate, although it doesn't really contribute to any of the other quantities. So that's sort of a dilemma. On the one hand, you see you cannot avoid this factor. On the other hand, you see it's, in some cases, not really optimal. And Dodziuk was very aware of this, sort of, as I can. And then he just wrote another paper fixing this. And therefore I need a projector. Is there a chance to switch it on? So, because like in 2 years later, in this paper they wrote the following about this first, about this 84 paper. This results are somewhat unsatisfactory. The lower bound on the bottom of the spectrum depended not only on the isoperimetric constant h, but also on the number lowercase m, which is our capital M. However, it's intuitively obvious that such a bound is unnecessary. And in this paper, we modify the definition of the Hilbert spaces associated with the graph and fix the problem. So what does it mean fixing the Hilbert space? It means choosing another measure. And we looked at this measure which counted vertices. So there's another option on graphs. So you have two things, right? You have vertices and you have edges. So that's exactly what they did. So is there another? There you can switch it off again. For a minute. So changing the measure. So what is the volume? If we go back to this volume part 2, it's counting edges. And volume deck of a set. And the way you can do it is if you sum over the vertex degrees in a set. And what is this? So if you sum over the vertex degrees in a set, then, well, that's actually the number of edges which emanate from X. So you get all the edges which are in W twice, because you count them from one direction and then again from the other direction. And you count the edges leaving W once. So in this sense, sort of this, if you sum over the degree, you count the edges in W. And this gives you a Hilbert space, the scalar product, sum over f of x, g of x, and then you have sort of this volume, which is now the vertex degree, and you have to the volume deck. And the Laplacian you get is very similar, however, it has this additional factor in front of the sum. So, and that's this Laplacian. So you see now, well, that's that cancels with this term. That's why it's a symmetric operator on this Hilbert space. And like the degree is also like the number of terms you have in the sum. So that's why it's called the normalized Laplacian. You normalize by the number of terms you're adding up. And this has another nice property, because you actually don't need functional analysis. This guy is always bounded. So bounded by 2. So you can see this here. So like the most basic estimate you can do is sort of getting 2 in here, and you get a plus, and you get a 2 in front. Then you have to look how many terms you sum up in this double sum. That's just the vertex degree. So, and then you have this term twice. This cancels with a 2, but 1, 2 remains. So that's how you prove this operator is bounded. And so what's different for this operator? Well, you look at again what is the Cheeger constant.
What is the what's replacing your integral of gradient f?
Sorry?
What's replacing the integral of gradient f squared? What's your new sigma? What you just erased? What is it?
That's the same quadratic form. It's the
Okay.
same quadratic form, you just restrict it to a different Hilbert space.
Okay.
Right, so and then you say, well, what is the area here? Well, since you're counting edges, you just sort of say, well, just take the number of edges leaving this set. And then your new Cheeger constant is again the infimum, and now with this new area, maybe I'll put an edge here, I had a V here first for vertices. And I have this different volume. And
It's the volume of W and
sorry, yeah, this is volume Jack, right? So it's the volume I chose, and then we have this theorem by Dodziuk and Keller. That was 86, and that tells you that the bottom of the spectrum of this new Laplacian, that's just h squared stack divided by 2. And here you don't have any more m. And if you revisit this example, then here, since you have a regular graph, so if you just divide everything by k, or k plus 1, you would divide this by k plus 1. Also the Cheeger constant would be divided. And now this is gone and everything works well. And also for like this estimate is not a problem now anymore. Right, so it gives you sort of sharp, also asymptotically sharp results.
So can you relate these ideas to doing a random walk on a graph where you go with equal probability to an adjacent edge?
That's exactly the Laplacian, which is sort of used by probabilists to model the random walk. You can say, well, this guy, where is it written? You can say, well, that's so if you pull out this term here, so if it comes out with a degree, so this cancels. So that's the identity minus the transition matrix for the random walk.
So that's the natural thing.
Yes,
Quite
so that's
natural.
it's a very natural thing.
Yeah.
So like, and the only thing how it sort of differs from the other one is sort of they have the same quadratic form, but it's on a different Hilbert space. Right. So here you're sort of counting edges as your natural measure. As I said before, you were counting vertices. And at this point, you could say, well, that's the end, because. And it definitely was for a long time. I think, like, if you look at papers on discrete Laplacians for non-regular graphs, the Laplacian which was used from then on was this guy here. So every geometer who did an excursion into the discrete world would use this operator. And when I started to look at these results, I looked at, I wanted to study the essential spectrum of these of Laplacians, and there's this result of Donnelly and Lee where they show that we have absence of essential spectrum when your curvature tends to minus infinity. However, this guy is a bounded operator, so it always has essential spectrum. So they're like this phenomena just doesn't appear in this way. However, I was able to prove an analog for the Donnelly-Lee result for the other Laplacian, which can be unbounded. And that was how I got in touch with Dodziuk, where he sent me his papers, because as you saw, they are still written with typewriters. They were not available on the internet. So, and it really bothered me since then, because from my background, I was raised in random Schrödinger operators, and there the sort of the operator they always looked at were not the normalized Laplacian, but the other one. So, and I felt that this thing here, this M, it shouldn't be there, but it was also not clear like how to get rid of it. And then when Radek started to study like this stochastic completeness on graphs, he also looked at this other Laplacian with a vertex measure, and then he realized that you get actually very different results in terms of volume bounds when you can ensure stochastic completeness. So we had example of cubically growing graphs which don't emit a uniqueness for a bounded solution of the heat equations. While in manifolds you need much stronger volume growth to get this non-uniqueness. You need super exponential volume growth. And in this context, sort of, this whole question arose: what's wrong with this Laplacian? And so what's going on here? And so is it really that you just chose the wrong measure, that there's only one volume which should be considered, or is there another ingredient which goes in here? And one thing which sort of started to shed some light on these things was this notion of intrinsic metrics, which you have in like the context of like weighted manifolds or on regular Dirichlet forms, that you define a metric which sees the space through the eyes of the operator. They don't use like the geometric notion of a metric, but you sort of like put yourself into the operator and look how the operator sees the space. Or you can also say how the point in motion, the related process, like how this one perceives the space. And that was like very well developed for local Dirichlet forms. That these are like sort of like energy forms which satisfy a chain rule. And Dennis Sullivan's told me so that there's like for this discrete one they don't have the proper Leibniz rule.
Yeah.
And you actually don't have a chain rule. You just have the mean value theorem, which is always a bad estimate. So and then my PhD advisor Daniel Lenz, and he was also bothered by this, and they came up with a notion of intrinsic metrics for non-local forms. So I think they were not so much bothered by these type of questions, but just by the question of how do you define like a proper notion of intrinsic metric for non-local operators which include graphs. And the solution they came up with was the following, and I don't want to present to you this definition for like the general context of non-local Dirichlet forms, but just for graphs in this very simple case. So that's a definition. A metric, or let's say, let's just say metric. You can actually define it for pseudo-metrics, but metric rho on V with respect to any given volume. So volume just that's just a positive function on the vertices. Like we have seen the counting measure, we have seen the degree measure. Now you just take any function. It's called intrinsic. If the following inequality holds, if you fix an x, or if you fix x in the sum over all neighbors, you take the square of that should be less than the volume. X. So this is due to, and it might have appeared in for jump processes before. I think Sasha Grigoryan can tell you the reference. I think maybe Uemura, Japanese people came with such a notion for various jump processes. So what does this mean? So you could also say that's equivalent that the gradient, and now I sort of make a definition of a gradient square, which is sort of the volume of x, and then you have rho x. Just need two. So this metric has sort of two ingredients. So I fix a base vertex O, and now I take this at x, and then I have O here and Y. And that this guy is less than 1. the gradient of the metric with a fixed space point is less than 1. That's equivalent. Or as you can also say it, that the Lipschitz functions, Lipschitz-1 functions with respect to this matrix, they are included in the set of functions with gradient less than 1. So for manifolds, you have an equivalence here. You have an equality here. For graphs, you can show you actually never have, well, never. There's like this, the one-edge graph. There you have like equality. Otherwise, you always have a strict inclusion. And the reason is just sort of like this is close to not taking maxima. For graphs, that's not close to not taking maxima. Right. So you have this notion of intrinsic metrics, and I think there was this time when sort of they came up, and there's work by Zahar Goyal and Jun Masamune and Chiping Huang, who used this for stochastic completeness and to start to get results in this direction, which showed if you look at a metric which satisfies this property, these problems start to disappear. And by start, I mean sort of like, it was sort of a process to learn how to use them and to adapt proofs properly. And then there was a question, can you use these type of metrics also for these Cheeger estimates? And that was like one summer when Radek visited Jena back then, and he would ask me this question, can you actually do it? And then I spent like afternoons to explain him why it doesn't work. So it was like several afternoons we discussed about it, and then I threw these examples and showed him that it doesn't work. And when Radek was gone, then Frank Bauer, he was a postdoc with Jürgen Jost, visited the week after, and he asked me the same question again, and I explained to him how it doesn't work, and then I realized, okay, well, my explanation is actually wrong. So it does work. Let me show you two examples of intrinsic metrics. Then we will see how we can use them.
Do you not need a factor of 1/2 in your gradient? It should be 1/2 volume of x. You should still have the same problem as before, but you're summing.
Somewhere this 2 appears, right? At the end, somewhere it appears, right? So like as I prepared the talk, I know where it appears. If I put this 1/2 there, then
Okay.
So let's look at examples. So let's say this example of the volume, which is just sort of the counting measure. So here you have the following. If you sort of take two vertices and you connect them by a path of edges, right? So you have, maybe you have x0 here, then you have x1, x2, x3. So you take the infimum over all paths. And then you sum along this path. So what you do is you take the vertex degree you take the maximum of the vertex degree at xi and xi plus 1. And you take the minimum because you take 1 over the vertex degree. You take the square root here, and you see that the following. So if x and y are neighbors in this case, then you sum over. You fix x and you sum over all the neighbors. So what happens? The first thing is you can drop this ins here, right? If there are neighbors already, you just make it larger. The second thing is you take a minimum here, so you can actually decide that you take the deck of x. Right? And then you square it, so you have 1 over deck x here. But like the number of neighbors, that's actually the vertex degree, so that's 1. And that's your volume. So what does it mean? It means 2 vertices are the closer, the larger their vertex degree is. Like actually it satisfies that one of those vertices has a large degree. So these 2 would be really close, while these 2 would be really far. And why is this reasonable? Well, if you look at the Brownian motion, or like at the jump process, so this heat particle, or this random walker, in continuous time, he jumps the faster the higher the vertex degree is. So if the vertex degree is the exponential rate in the holding time of this Brownian motion. So from here to here, the particle jumps much faster than it would jump from here to here. So in this sense, this is sort of a metric which sort of has an idea of what the continuous time random walk does. And of course, so if you have to take this minimum because you want it to be symmetric, that's. Let's look at another example. If you have this decree, you count edges, and if you look just at the combinatorial graph distance, that's just the number of edges you need to get from x to y. So if you look at this guy, at this metric here, which would be sort of the standard metric that's the first metric you use on graphs, right? So,
Infimum.
yeah, sorry. No, you take the infimum. So what you have here, if you just sum them up, well, they are always 1, right, if they are neighbors. So you just have the sum of 1s. That's the vertex degree. And, well, we don't even have an inequality here. Right? So that's sharp. So the thing is that this combinatorial graph distance, which is sort of the natural distance, or the first distance you come up with, is actually the correct distance for this volume measure. And that's why everything worked for the normalized Laplacian. Because all quantities, like when you talk about volume, or also about this Cheeger constant, the distance you use is this guy here. And of course, like if you do spectral estimates, you can say, what is the bottom of the spectrum? Well, that's sort of the exponential decay rate of the heat equation, or of the heat kernel. And so this should somehow involve a distance which sort of like which is like how the heat sees distances. Right? And so now we can ask how does this intrinsic metric, this like combinatorial distance, actually enter this quantity here? So you cannot do anything about the measure, right? That's fixed. Right? So the measure we fixed is already. So it has to go in here. So if you look at this definition here, we could also say, well, it's sort of the sum over all boundary edges, the sum of 1. But instead of 1, you could also say, right, the sum of this distance here, which is always 1. So that's how it's hiding. So now all you have to do is to replace this guy here with an intrinsic metric. And so we can maybe do this here. So for rho intrinsic, I think like in some papers, like it's called adaptive. That's a different name. Define the area with respect to this rho, the boundary, by just the sum of the boundary edges in here. And that would be sort of like one example you can use. So if that's sort of the explicit metric, you can always write down. In some cases, we can come up with an example where this is like, you can even improve this a bit, where this is not sort of the optimal one. But that's sort of like a good candidate. And then, well, with this one, you define your H with respect to rho as sort of this area with rho, and by the volume. And then the theorem, that's the theorem with Frank Bauer and with Radek. Prove that for this Laplacian, where we have the vertex measure, we can estimate this from above, from below, by this Cheeger inequality. So in here, sort of like this bad constant is gone. So how did it disappear? It sort of went in here, right? Sort of like here you have this vertex degree. If you take this example, this vertex degree actually goes in here, but it doesn't bother you as much because like the place where you sort of minimize your Cheeger constant, that's also where you count this degree. So in this example before, that would give you now the right estimate. And you can do the same thing for weighted Laplacians. Right? If you have now a Laplacian, which is sort of like you have an Ash weight and maybe an arbitrary volume. So you have the volume here. Like that's just any function, any positive function. And you take all neighbors and you take an Ash weight. So like these type of Laplacians, then you just put your weight here, right? And then sort of everything works. And like the whole proof also works for general jump processes. So that's it's actually the same proof. So and that was sort of something we were like very happy about. Because now it's not sort of that you have like this one Laplacian which is the correct one. Right? So if you don't have to choose what is sort of like, or you don't have to make this choice, like there's like one natural choice and everything else is sort of either given or you sort of just don't get the results. But it's now more like that you sort of you choose like your energy form, then you choose a measure, and then you have to choose a metric, which is sort of the correct metric for this measure. You can also go the other way around. You choose a metric first, and then choose a volume. So that's what like maybe probabilists would do. They say just the volume is just sort of the speed of the random walker. So you have some freedom in this. And maybe that's a good point to stop. And I can share everything else privately.
Question?
Can you explain the other problems that it fixes again, like the where you want the form to be where you want it to be unbounded, the operator?
So one example is of stochastic completeness.
So we'll talk about this tomorrow.
Yeah.
That's actually my talk.
Right.
Don't give away the punchline.
So another thing is where it fixes, for example, that the bottom of the essential spectrum of the Laplacian can be bounded by some mu square over A, and mu is sort of like the lim inf maybe over the volume of force, right? So if you say, let's ln divided by r. That's the exponential volume growth of your graph. So it tells you if you have sub-exponential volume growth, then your bottom spectrum is 0. And if you just take for this force here the standard metric, then again you have sort of quadratically growing graphs or cubically growing graphs which have positive volume of the spectrum. So you have, well, like very slow volume growth, but the bottom of the spectrum is positive. However, if you sort of define these force with this other metric, then you get like the correct estimate again. There are also criteria for recurrence. So it's like that with a certain volume growth, you're recurrent. That would also work. Also, this question of essential self-adjointness. So, if like a manifold, if the manifold is complete, then your operators they only have one Laplacian, one self-adjoint realization. Right? And if, like with this with the combinatorial metric, every operator, every graph is complete because you have discrete space. However, not every Laplacian is essentially self-adjoint. So I think there are these type of questions which can be answered along these lines.
Yeah.